Hello, John here, M0JPI. Today's video is about AI recognition on the Red Pitaya using Edge Impulse. In this video, the second video in the series, we'll talk about artificial intelligence signal classification. The first stage is collecting the training data, which happens on the Red Pitaya board. The second stage is creating and training the model, which happens on the Edge Impulse cloud on the internet. And the third stage is the artificial intelligence signal classification inference, which happens just on the Red Pitaya board using the Edge Impulse model that's been downloaded from the internet. Once you've trained the model and training is complete, you no longer need the internet connection, and the Edge Impulse model can do inference just on the Red Pitaya board itself. So this video shows how to use the AI inference system from Edge Impulse once you've already set it up and you have a model file. So to begin with, I'm going to use inference, which just uses the model file and the sound file, and so I don't need to have a hardware setup. But for later on in the video, I'll show you what the hardware setup is. So I've got two diagrams here. On the left, I've got the hardware, and on the right, I've got what the software is doing with that. So I've got a microphone is attached with an amplifier to fast input 2. The setup for this is in my Fast ADC video if you want to see how I've set up my Red Pitaya board. But it can sample at 125 megasamples per second, so you could have radio signals, or you could have all sorts of very fast input signals coming in here. I'm using audio because it's easier to demonstrate, and the Edge Impulse has got lots of examples on audio, but it can use any kind of analog data. It doesn't have to be audio, and it doesn't have to be one channel. Edge Impulse can process multiple channels at the same time, so if you have an event where it's easier to see it if there's multiple inputs, that works fine as well. You could also send data from the 1 kilo sample per second analog or the digital IOs combined as well if you wanted to. So it doesn't have to be the fast analogs, but I've just used them because they seem to show the ability of the Red Pitaya board best. And then importantly, we've got an SD card that saves all of our files, and then we've got a chip here that's got a combined FPGA and dual-core ARM A9 processor, and we've got some memory. And then we're also using a web browser and the internet to get and receive data. Well, once you've set it up, you don't actually need your internet connection anymore. So the first video that I did used the internet quite a lot, but this video doesn't need the internet. It's all done locally on the board. So the software setup is the sound file comes in, the sound file gets saved to the SD card. We already have float wave test raw sound file over here, and we can get Jupyter notebooks coming from GitHub, which I showed in the previous video. And the model file, which I also downloaded from the previous video, is coming from the Edge Impulse project. You can just make a copy of my project and use that as a starter for your own project. So because we already have a sound file, I'm just going to run this example. So if I click on a cell and press Control and Enter, it will run this Python program for me, and it will run it one cell at a time. So on the left hand side we've got cell numbers, so when it's a star or an asterisk it's showing that it's running, so it's importing those libraries now. And then because it's our first cell, it should say 1 when it's finished. It does show previous run results before, so these are the results from last time it was run. So I had a problem the first time. I'm not quite sure what it was, but if you go to kernel you've got different restart kernel options, and this restarts the Jupyter system for Python. So you can restart the kernel, you can restart and clear all the output, which clears all these, or you can restart and run up to a selected cell or run them all. I'm going to go with restart the kernel, and it leaves the output as it was. So this output will get overridden. So if you click on the cell, press Control and Enter, and it will import the Python libraries that we need. So once they're imported, you can see when it's running you get a star, and then when it's finished you get a number. So after this I'm just going to set up all the files to make sure it points to the right files that we're using. At this point it checks the model and checks that it's the right M0JPI model. If you've copied this, it should say your username, and then it says the labels that we've got. So it can either detect background noise, edge impulse, or Red Pitaya. And then here we've got the version number. So there is actually a sample file already as part of my GitHub project. So if I run the classifier, it's 99.62% sure that it's Red Pitaya. You can actually get more details on that, so there's zero probability of the other two, and then again you can get more results. It shows you all the different details about that. So that's without the audio setup, how it works. It doesn't need the internet. Once it's got the Edge Impulse set up and the GitHub set up, all it's doing is, well, in this case it actually used an audio file already from GitHub, but it would use the audio input, process it on the board, and give you the result. And it can produce the result very quickly. So that was 26 milliseconds, and that was using the CPU, the ARM9 CPU, 26 milliseconds to decide. All on the board. As again, I was using audio input. You could use any kind of fast input, or you could use the slower 1 kilosample per second analogs, and you could combine analog and digital together if you wanted. So that's a nice little demo of how it works. I will show you the other one. So I have two other files. One is classification using the audio system. So this needs a bit more code loading because I'm going to load the audio as well. So I'm going to run this one. This will actually use the FPGA overlay. And I might get a problem because I'm running the other example at the same time. We'll see if we do. If we do, I'll show you how to close down the other one. And if we don't, I'll run the example and show you how to close it all down at the end. I think that worked okay, but if you've already got an overlay running, you might need to close them down before you start, but that looked okay. So this is setting up our board. So we're using quite a high amount of decimation because it comes in at 125 megasamples per second, and I want to send 20 kilosamples per second to Red Pitaya. So it does quite a lot of decimation to reduce the amount of samples down to 30 kilosamples per second, which is within the audio range. So then we set up the functions, again point it to the model file and tell it where to save, so it'll overwrite this sound file. Check that we've got the right settings for the model, which we have, and then we do it. So I'm going to say the words edge impulse. I hope that it detects that as edge impulse instead of Red Pitaya. Edge impulse. That did not work. Edge impulse. Ah, there you go. So it depends on how much training data you've got, and how. I think what the problem I've got here is something called overfitting, where you've got a lot of training data that's very similar that causes a problem where it gets very confident. So the solution to that is to try it with different voices and different people and different times of day, different microphones and things like that. But I'll see if I can get it to do Red Pitaya. Red Pitaya. There we go. But you see, it's very high in confidence, 99.99%. That's probably overfitting the data. Let's try Edge Impulse one more time. Edge Impulse. There we go. And background noise. There we go. So it does work. There is a bit of overfitting where it gets overconfident and produces the wrong answer. But as I said, the solution to that would be more samples, different samples for different people, different microphones and so on. It's the same for whatever data you're feeding it. So if you're feeding it radio data, again, it will be different types of radio data, different antennas and different ways of producing slightly different variation in the input, and then that would reduce the overfitting problem, which I think is what was causing the problem the first time. You can get more details of the results, so like how long it took and things like that, and then you can print those nicely. So it took 26 milliseconds again. We can actually produce plots of the, well, this is background noise, so it's not going to show you very much. This is a plot of the background noise. If I try it again, I'm going to try Edge Impulse again. Edge Impulse. There we go. We're still getting Edge Impulse. That's what that was, Edge Impulse. As part of the Python audio display, you can actually play back the audio as well. Edge Impulse. So that's it. That's my example. I have another notebook. This notebook is to record data and add it to the training set. So in your project, we've got data acquisition, and then we've got all of the training data here. So you can use this to add more training data to the system. Now, the system doesn't like having multiple things open at the same time because they'll all try and use the FPGA. So the best thing to do is close them all down. If you go to the running terminals and kernels, you can shut down all of the kernels and then go back to the files and just open the one you're interested in. So this is the, goes down the launcher. This is the input. So this is to collect audio samples. So it could be any samples, but I'm going to use audio samples and send them to the Red Pitaya Edge Impulse project. So you could see these all came in on the 1st of September. It shall say today, back a new one. So that's loaded the FPGA, set it up, setting up decimation. Right, now, what was I sending as? So it says send it as Edge Impulse. Forward Edge Impulse. Edge Impulse. So we should have to see what it looks like. Save it. And then this is the upload, and then it should say upload successful if it's all worked. Right, okay, this is an interesting problem. So, you need to have a file called app keys. So I've created an example here. So this is the example file of the kind of thing it should look like. But each of the project's app keys are different. So if you go to dashboard, in your project where you go to keys, you'll be able to see the keys, and it will show you a key that looks something a bit like this. Well, it's not going to be 1, 2, 3, 4, 5, 6. So to avoid me putting my actual app keys into GitHub, I've just made a sample file that shows you what they look like. So I'll set up my actual keys and then come back to this. So I've made a folder called appkeys.py. So it follows the sample keys example, but gets the actual keys from, if you go to Edge Impulse dashboard, if you clone the project and go to keys, you should have your own keys in there. So if you make a file called app_keys.py, have a format it like this, but with the actual keys in here and here, then if we click on this cell and press Control and Enter, and then it works this time. So, yeah, we've all got our own different app keys, so we just need to make a folder for that. And then that's a shorter version of it. These are shorter versions. So this one here is just background noise, so if I don't say anything. And then I could do it again with, change the label to Red Pitaya. Red Pitaya. That's all done, so we should have 3 files that should now appear in our... Yeah, so we've got 3 files in our Edge Impulse system, and you can see these are today's files. Because we've changed the data, it's now telling you to retrain the model. So we've got, if you look at the dashboard, this is how the system is set up. So we've got a description of the system. I've set it to target the Raspberry Pi because it's a similar board to ours. It's a Linux Cortex board, Cortex A glass board. So we're using Cortex A A9 processors in the case of the Red Pitaya. So we choose what we're targeting. We have all the data samples. It wants you to put some of them in training and some of them in test. I'm going to leave these ones in training for now. If you wanted to change them, you can highlight them and you could move some of them to the test set, or you could disable them if you wanted to just not include them for now, or you could delete them altogether if you didn't like the samples that were done wrong. If you go to experiments, there's a really good tuning system. If you just run the Eon tuner, that really helped me get the accuracy up to 100%. But it did overfit it slightly, as you saw in one of my test runs. So if we go to Create Impulse, this is where the setup is. I wouldn't worry too much about these sliders because the Eon tuner in experiments will actually set all these for you. So you can just go with the defaults. I've gone with the FCC processing block because if you look at the examples, it says that works best for human voice. So that's what I'm doing in this example. But if you had other types of data, you could use other types of learning processing block. For example, spectrogram could be good for some of your projects. And again, for learning blocks, I've used classification because it's great for audio. But if you had different types of data that were useful for other things, for example, aggression is great for numeric continuous values, you could choose them instead. You can actually have more than one, so you can actually have 2 if you wanted, and you could do both of them. And then the output features are just how many labels you're going to go for. Once you've done that, you can choose all the parameters. Again, I have just let them
I've just let them go for the default. If you are using the enterprise version, you can get it to auto-tune it, but I found the default seemed to work fine. And angle line classifier, I've just used the defaults. These, the Eon tuner will change these. It does a really nice description of it, so you can see here, these are the edge impulse samples. These are the ones that Red Pitaya, and then these are the background noise ones, and it's separated them all out. And if you've got a clear which ones are which, if there's a clear separation between them, that makes it more likely you're going to get an accurate result. And then here you can see how accurate it is for each one, and we're getting 100% on each one. Not quite right, because one of them was wrong before, but that's probably because I didn't do enough training data. If we retrained it now, it might actually work even better than before, because we've now got 3 more samples. So if you just press training, it will start off with the audio MFCC or whatever processing block you've used. Then it'll go on to the learning block, in our case classifier, and then it will actually try your training data against the impulse and see how good the model is. So I think this is really good for someone like me who isn't a data scientist. I'm a normal software engineer. I know more about Python than I do about data science. And this, it gives you recommended settings. The Eon tuner does a lot of work, and it's free to try and experiment with them for students and learning. And even with learning within a company, you just can't use it commercially or to add value to your business unless you pay for the developer version or the enterprise version. It's got good documentation as well. If you look at the documentation while we're waiting for that to finish, this is all the documentation. There's video tutorials, there's a description of the edge impulse for Linux. I've generally used the Raspberry Pi examples because the Red Pitaya has a similar Cortex CPU, so the instructions mostly work the same. And it also shows you how the Python library works as well, Python SDK. So both of those are similar on our board. See if it's finished it yet. Oh, it's doing model testing now. So it's done it's built the model, it's now just testing it. Let's hope it passes. It's not too bad. If you don't get 100%, probably like 99% or 98% is probably better, because if you're getting 100%, you might be what's called overfitting the model, which is the only thing I know about data science, where if it's 100%, it maybe is too good. If you're getting 99%, 98%, that's probably better. Don't know if it tells you anything about overfitting in here. There you go. Increasing model performance. Yeah. Number 1, do more training data. How's it doing? Oh, it's finished. Right, so if we go to model testing, it now tells us how good. Oh, it came out 100%. And again, we've got a feature explorer slightly different to the one on the classifier. Oh, interestingly, it's showing one incorrect, but our training... that must be one that I've added. Yeah, so it's saying that it's now not 100% accurate. The reason why we're getting 100% on the testing is because if we look at the data that we've got 108 samples in training and 45 samples in testing. So when that model testing gets 100%, it means the 45 samples are all passing, but one of our training data, I'm guessing it's this edge impulse again one, is not passing. If you ran the Eon tuner and ran that again, which I'm not going to do because it takes quite a while, if you ran that, you might get back to 100% accuracy. That's what I've done in the past, where I've trained it and it's given me something similar to this, where I've got like a 10% error, and then if you put more data in, go to the Eon tuner and choose 100% accurate. Make sure you do the validation and the test data sets, so 100% on both. And then if you do the download the model again, which is in this file. So if you do edge impulse, Linux runner download model file EM, it'll replace that. Instead of version 17, you get version 18, and then you get more accurate. So the more data you put into the system, the more accurate it is. At the moment, we've got, so it does it in 5-second samples, and overall we've got 13 minutes and 56 seconds of data. So it's not that much data. If we added more, it would be more accurate. So I hope you like my project. So that shows inference on the Red Pitaya using Edge Impulse's system. As I said, it's free to experiment with. If you are adding value to your business, you need to get either an enterprise or a developer license. But I found it really interesting to make this project, and I was surprised how fast it was. So it only takes 26 milliseconds on the CPU to do the inference for 5 seconds of audio. I trained it on 3 different sets of words, labels, and you could do more than that if you wanted. And again, you don't have to do audio, it'll take any kind of analog data, and you can combine analog and digital data as well, and you can combine more than one channel. So if you wanted to, you could combine, say for example, 2 fast analog inputs and 3 1 kilosample per second analog inputs, and you could even do an audio, a digital input. You could send all of those into the Red Pitaya model. And what I like is all of this training system is done via the internet, but once the training has happened and the model is downloaded, then the actual inference happens on the board. So you don't need an internet connection. Once you have finished training your system, you can disconnect it and run it offline, which I think is really great. So I hope you liked my project. Thank you very much.